Hello students, this is lesson U5A02b. By the end of the lesson, you should be able to say, I can solve for sides and angles between similar triangles. So I have not given you a formal definition for what similarity is yet. So let's do that right now, actually. We've been working on a working definition. We have some sense of what similarity is based on previous lessons. You've worked through U5A02a, which was a pretty rigorous exploration on the properties associated with dilations. And as a matter of fact, all the properties that you found is, in fact, definitions for similarity. So what exactly is similarity? Or how do we know when two figures are similar? Well, two figures are similar if one is the dilation of the other. That's it, okay? However, that right there, okay, has a ton of different properties, as you saw in the previous exercise. When you dilate something, okay, we know a lot of information about the corresponding side lengths and how they should be proportional. Not only the side lengths, but also the perimeter as well as the area, right? They all follow some strict rule directly related to the scale factor, which is the factor in which we're dilating by, okay? And all of this, okay, is circling back to this concept of similarity, okay? So how do we show whether or not two triangles, okay, we're going to start off with just talking about triangles, as this is one of those fundamental building blocks to talking about polygons, okay? So a triangle, two triangles, okay, can be thought of as similar, okay, when all the angles are going to be congruent. Wasn't that right? That was one of the things that we had come up with, okay? When we dilated two triangles, well, when we dilated a triangle, as it turned out, all of the corresponding angles ended up being the same. And the two triangles are, again, similar, right? Is it absolutely necessary that we need to know all three angles for us to determine whether or not the two triangles are indeed similar? We actually don't need to know the third one, because if the two angles are already congruent here, then it can be implied that the third one has to be congruent, right? So we only need, at most, two pairs of corresponding angles to show that the two triangles are in fact going to be similar. And because of this is a theorem, okay? Because we just went through the logic of explaining why we only need two angles. We call this the angle-angle theorem, and that is all you need to show whether or not the two triangles are similar, or whether or not one is the dilation of the other. Are there other ways in which we can tell whether two triangles are similar or not? Absolutely. There are actually two other ways. So let's take a look at this one here. And I wrote over this. Let me just erase that because I want to talk through it again. So if you notice right now, I have one pair of corresponding angles over here. As it turns out, if we have two pairs of proportional corresponding side lengths, then that would be enough to show that the two triangles will therefore be proportional. So if I have side length W corresponding to side length A is proportional to side length X to side length B, I do not need to know any information about that third side here. I do not need to know anything about the third side of whether or not those third sides there, okay, are proportional, simply because I already have the information about the angle over here. So this is yet another theorem. We call this the side angle side similarity theorem, because I am comparing a side to an angle to yet another side. This is the side angle side theorem, similarity theorem. The third possible way of showing two triangles are similar, if we know nothing about the angle measures, is to show that all corresponding sides are in fact proportional. So if I have triangle ABC and it is similar to triangle WXY, I do not need to know whether or not any of the angles are congruent. All I need to know is whether or not all three sides proportionately share the same scale factor. And if they do, we call this a side-side-side similarity theorem. Alrighty, so my mistake there. I should have erased what I wrote there before showing this, but let's take a look at this, okay? What we want to do with this is I want you to determine whether or not the triangles here are actually similar or not, okay? So pause the video to see if you can figure this out. Hopefully you guys had some time to think about this. Upon inspection here, I immediately noticed that the missing angle there is 75, and the missing angle over here is 48. So yes, all the angles are in fact congruent to one another, so therefore these two triangles are similar. One is the dilation of the other. These two triangles are similar. Are these two triangles over here similar? As a matter of fact, they are, because I have a pair of parallel lines, and these are alternate interior angles. And last I checked, I have two corresponding congruent angles, and yet again, this is going to be angle-angle theorem. So both of these triangles, or both of these problems A and B, both of them are going to be similar because of, again, angle-angle theorem. Let's take a look at this. So here we are going to determine whether question A and question B, whether the two triangles in those two questions are similar or not. So let's take a look. We're going to compare all the corresponding side lengths in size order from smallest to largest. Pause the video to see if you can figure this out on your own. So so hopefully you guys had some time to think about this. If I compare all the side lengths in the smaller triangle, placing it in size order, so I'm going to have 5, 6, and 8. And I'm going to compare it with all the side lengths in size order in the larger triangle. So I'm going to 12.5 to 15 and 20. Let's see whether or not these are actually all proportional to one another. As it turns out, it actually is. All of them equal to 0.4. So I can say that the two triangles are in fact going to be similar based on side-side-side similarity. The next problem here, if you notice, okay, these are we actually have two triangles overlapping one another. I have a smaller triangle inside of a bigger triangle. We're going to see whether or not these two triangles are similar. And the way in which we're going to approach this is, if you notice, there's no information given about that third side. Do we need to know whether or not that do we need to know the dimensions of that third side? Actually, we don't need to, because if you notice right here, both small triangle and a large triangle, it's sharing angle A. And so if these two triangles were to be proven similar, we would use side-angle-side similarity. We're going to compare this side over here with this side over here. So let's see if it is or not. I'm going to compare the longer side to the shorter side. So I'm going to compare the longer side to the shorter side. I have 8 plus 4 to 10 plus 5 over 8 and 10. And as it turns out, they are indeed going to be 3/2 of 3/2. So yes, these two triangles are similar because of side-angle-side similarity. Let's take a look at whether these two triangles are similar or not. And again, I'm going to compare based on size order again. I'm going to compare the two triangles. I have 6 to 4, 4.5 to 3, and 3 to 2. And then as it turns out, they are indeed all equivalent to 3/2. So yes, these two triangles are similar because of side-side similarity. I also know that all the corresponding angles are going to be congruent. I know that Q will be congruent to L, K will be congruent to P, and angle L will be congruent to, and angle R will be congruent to angle S. Pause the video to see if you can determine whether or not these two overlapping triangles are similar or not. So again, hopefully you guys had some time to think about this. If I were to compare the two triangles, I'm going to try to prove this using side-angle-side similarity, because I recognize that angle A there is congruent to itself. So because of this, okay, I now need to compare this side length to this side length. So I can say AB over AC, is it or not, is it going to be equivalent to AE over AD? So AB is 2, AC is 4, AE is 2, and AD is 3. Last I checked, 2/4 is not the same as 2/3. So the conclusion that we can draw from this is triangle ABE is not similar to triangle ACD. All right. Next. Sorry, this was not a part of the original problem. Let me erase that. Pause the video to see if you can figure this out on your own. What we're going to try to do is to solve for the side length SU and UV. And welcome back. So hopefully you guys had some time to think about this. These two triangles are in fact going to be similar because these angles over here are going to be congruent because of vertical angles. So now what I have is I have two corresponding pairs of congruent angles. And yes, these two triangles are going to be similar because of angle-angle theorem. So knowing this fact, I can then establish some proportions. I know that SU to UV will be the same as UT to UW. Let's substitute in the values that we know. So I know that SU is x, UV is 2x minus 1, and UT is 3, and UW is 7. I'm going to cross multiply, distribute the 3, subtract both sides by 6x. Finally, x will equal to 3. Our goal was to figure out what SU and UV was. So I'm going to substitute what x is back in and figure out what is the length of SU and UV. So SU will equal to 3, and UV will equal to 7. All right, so let's take a look at this. This next problem here, pause the video to see if you can figure this out on your own. Hopefully you guys had some time to think about this. Our goal is to figure out what is IL and JK and HK. And if you notice immediately that we have two right angles and there's an overlapping angle H. So these are overlapping right triangles. And these overlapping right triangles are indeed going to be similar because of, again, angle-angle theorem. So I can establish the following. That I will need this. I will need side length HJ because I need to compare the smaller triangle with the larger triangle. I know that HJ is equal to 5. And I also know that HI is equal to 3. So immediately the scale factor going from small to large is going to be 5/3, or the other way around, from larger to smaller is going to be 3/5. However, I can illustrate this a little more clearly by writing out the proportions. HI to HJ will equal to HL to HK. So I'm comparing the legs to the hypotenuse. All of this should be proportional. I need to find out what HK is, right? So let's do that. So I want to substitute in all the values that I found, which is HI is 3, HJ is 5, HL is 4. That leaves me with HK. HK, as it turns out, will equal to 20/3. That's the length of the hypotenuse. So our goal now is to find out what is the length of IL, and then lastly, the length of JK. So I'm going to find out what IL is first, and then after I find out what IL is, I'm going to set up a proportion to find out what JK is. So recognizing that triangle HIL is actually a right triangle, I can set up Pythagorean theorem. I know that HI squared plus IL squared is equal to HL squared. I'm going to substitute in all the things that I know. I know that HI is equal to 3. IL is unknown. HL is equal to 4. I'm going to solve for IL. IL squared, as it turns out, will equal to 7. So therefore IL will equal to square root of 7. Let's now use this information to find out what is JK. So to find out what JK is, I'm going to compare IL to JK is to HI to HJ. So I know that IL to JK is square root of 7 over JK. which is equal to 3/5, because hi to hj is 3/5. If I cross multiply to solve for jk, I would have end up with jk is equal to 5 squared root of 7/3. If you use the Pythagorean theorem to find out what jk is, you will arrive at the same conclusion here. Let's take a look at another example. So here in this case, I have, let me erase that. Pause the video to see if you can figure this out on your own. I have triangle ABC and triangle XYZ, and you're given the information here. Pause the video to see if you can figure this out. So hopefully you guys had some time to think about this. Now this problem here is written rather tricky. So angle A corresponds with angle X. Angle B corresponds with angle Y. And then angle Z corresponds with angle C. It is really important, okay, that you are aware of this, so that when you are labeling the diagram, that it corresponds correctly. So angle B is equal to 46. Angle Z is equal to 44. So if this is true, okay, and I know that AC is equal to 8, XZ is equal to 12, okay, what I need to do now is I need to figure out all the different angles between the two triangles. It looks like it's an impossible task, isn't that right? Well, actually, it's not that impossible, because if you look at this, if angle Z is 44, what would angle C therefore equal to? Angle C therefore would also be 44, wouldn't it? And if angle B is 46, if angle B is 46, and angle B corresponds with angle Y, isn't angle Y then 46? And if angle A and X are corresponding, and I know that the other two angles are 46 and 44 apiece, then that means angle A and angle X must be 90 apiece then. They must be 90 and 90. Because I'm sorry, not 90 and 90. What am I saying? 46 and 44. Yes. I was second guessing myself. They do indeed equal to 90. Because 90 plus 46 plus 44, they all add up to 180. Okay, so now that we found all the angles for both triangles, how much bigger is YZ than BC? Okay, so what we need to do, and again, we need to compare how much bigger is YZ bigger than BC. Well, I know that this is also proportional to XZ over AC. So therefore, this is going to be 12 over 8. Or really, this is going to be 3 halves. It's going to be 1.5 times bigger. YZ to BC, YZ will be 1.5 times larger than BC. So again, YZ will be 3 halves times bigger than BC. Okay, last question. And we're looking for, well, pause the video to see if you can figure this out on your own. I know that AB is parallel to CD. I also know that BC is parallel to DE. So I have a bunch of parallel angles happening here. So because I have a bunch of parallel angles happening, I know immediately that these angles over here are alternate interior angles. I also recognize that these angles over here are also congruent because of alternate interior angles as well. So the smaller triangle and the bigger triangle, they are going to be similar because of, again, angle-angle theorem. Our question here is to find out what is AC is what proportion of EC. AC will be what proportion of EC. So in other words, how many times bigger or how many times smaller are those two segments? Well, in order for us to figure this out, let's find out what are all the corresponding side lengths first. So I know that ABC is going to be similar to triangle CDE. And this is because of, again, angle-angle theorem. I know that angle A corresponds with is going to be equal to angle ECD. I also know that if I substitute those values in, I can immediately solve for what x is. X, as it turns out, will equal to 9. And if I know that x is equal to 9, I can then solve for angle A and angle ECD. So angle A is 112, and angle ECD is also 112. Next, I also recognize that the side lengths ED to CB proportionately should equal to CD to AB. This must be 4/7. So again, ED to BC, because they are proportional, should be equal to CD to AB. We have 4/7 here. So knowing this, we can then say, ED, which has a length of 3, okay, to AB, CD to AB is going to be 3 to AB will equal to 4/7. I can solve for what AB is. AB, as it turns out, will be 21/4. So I solve for what AB is now. Next, I need to find out how much bigger is AC compared to EC. So again, understanding that all of these sides are proportional, we are going to be sharing the same proportion of 4/7. So therefore, AC will be 7/4 times bigger than EC. That's it.